Welcome back to the general relativity lecture. We will now start with our final larger topic, which is called the geodesics in Schwarzschild spacetime. This is quite a large topic, and we can't discuss it in full detail. However, it is an important topic because it also contains as a little side result the classical tests of general relativity. I'll discuss this more when we get to this. Let's begin to write. So we write ds squared, which is our line element, as minus f of r dt squared plus dr squared f of r plus r squared d omega squared, where our f of r was 1 minus 2m over r, which is the Schwarzschild line element, so that our Lagrangian is the following. We always call this thing capital L. This is the minus f of r t dot squared. Remember, my dot almost always means differentiation with respect to an affine parameter, r dot squared over f of r, plus, I now make explicit what the omega squared is, theta dot squared plus r squared sine squared theta phi dot squared. And our little reminder here is that L is minus 1 if we are interested in studying massive particles, and L is 0 if we are studying the motion of a massless particle. What you should be thinking here is light. Those two distinct cases are interesting from the point of view of what we are going to do. If you are interested to study the motion of a planet around the sun, the planet is obviously a massive particle. Hence, it makes sense to work with Lagrangian when L is minus 1. The other one is actually pointless, so that is the one choice we have to make. However, if you're interested to study, for instance, the trajectory of light that passes by the sun, you have to, of course, set L to 0 and work with massless particles or light. So both of these cases will appear in the classical tests of general relativity. What we are now doing, we are formulating the geodesic equations. You know there are 4 of them, 1 for each of the coordinates, and we find them by writing down the Euler-Lagrange equations for this Lagrangian. However, instead of just writing them all out, it is quite useful to do this systematically and in a very specific order. And if we do this in a specific order, it is reasonably easy to arrive at a final equation that is very manageable and contains quantities that we can understand well. Hence, our first equation is the first equation. So we begin with the theta equation. Let me remind you of our Euler-Lagrange equations. We have dl d theta, and this is d over d lambda dl d theta dot. Let me write this a bit nicer here. Dot L. dl d theta is easily computed This is not a function of theta, neither is this, neither is that. This is the only bit that is a function of theta here, which means we get 2 sine theta cos theta. This is the chain rule. You differentiate the outer function, you get 2 times the inner function and then the derivative of the inner function, which is the cos theta. R squared phi dot squared equals d over d lambda. And then we need to differentiate L with respect to theta dot. This is the only term that contains theta dot. We get here 2 r squared theta dot. We see immediately that the 2 cancels. You might have seen in some other textbooks that sometimes people put a factor of 1/2 in front of the Lagrangian. And they do this so that whenever you differentiate with respect to the dotted variable, the factor of 2 gets compensated by the 1/2. But because you have a function linear in L on the left and linear in L on the right, the Euler-Lagrange equations are scale invariant. So if you multiply this thing by any constant c, the constant will eventually disappear from the equations of motion. So it doesn't really matter whether or not we have a constant there or not. And the first observation here is that we can actually solve this equation immediately by just looking at, can we find a function theta so that this is always satisfied? What we need to look for is, if we chose theta to be a constant, then the right-hand side is immediately 0. Can we find a constant theta so that the left-hand side is also 0? Yes, one choice would be theta equals 0. That's not a good choice for reasons that have to do with our choice of coordinates. However, we can set theta to be pi over 2, and that is a very convenient choice. This equation is solved by theta equals pi over 2. Now you need to ask yourself, why is this expected? What we are actually doing is we are confining the motion of the geodesic to the equatorial plane. This means motion is confined to the equatorial plane. This is the same as in Newtonian mechanics, where you know that the two-body problem, which is really what we are studying here, think about this. We have a central object described by the Schwarzschild solution like our sun, and then we either study a massive or massless particle within this gravitational field. Hence, we have as such two bodies, and we can speak of a two-body problem. You know, in Newtonian mechanics, the two-body problem can always be confined to a plane, which is the statement which follows from this line here, saying that theta is pi over 2 means we can always choose coordinates so that the dynamics is confined to a plane. This is in complete analogy to Newtonian mechanics, and extends very nicely to general relativity. First of the 4 equations is solved and dealt with. Next, we look at the T equation. Note that the Schwarzschild solution is a static solution to the Einstein field equations. Recall we showed that every spherically symmetric vacuum solution is automatically static. There's no time dependence here anywhere. And this should have some implications for our geodesics and the geodesic equations that we are interested in. dl over dt equals d over d lambda dl over dt dot. As I already said, it is not explicitly a function of the coordinate t. Therefore, we get a 0 on the left. And if we differentiate our Lagrangian here with respect to t dot, what we get is minus f of r untouched, and here we get 2 t dot. We have a derivative here which we are not applying to the right-hand side, because we can immediately integrate this equation. Minus f of r to t dot. And because I already know what this constant of integration will roughly mean, I'm calling it minus 2e. The minus sign makes sense because we have a minus sign here. I can multiply through by the minus sign and then have plus as a constant of integration. But if I stick with the original equation, then I need to put in the minus sign. I discussed the 2 here, which is a scale factor that we can or cannot have in the equations. I don't like this 2, so I'm introducing my constant of integration as minus 2e. That is a constant of integration, and this means in particular that we have e equals f of r t dot. And this means we can write this e in the following way. If we scroll up here, we have that f is, you probably remember this, 1 minus 2m over r. So we get here 1 minus 2m over r times t dot. Why is this expected? This is expected. We have t independence, and this corresponds to a sense of constancy of energy. So Lagrangian is independent of time. Usually means energy is conserved in classical mechanics. And so we interpret E as energy, and I'm writing this in quotation marks because we have to be quite careful. If you look at this E here, it is quite clear that E does not necessarily have units of energy, which follows from the fact that 1 minus 2m over r is dimensionless, and dt over d lambda, lambda is a dimensionless affine parameter. This E here has something like units of time. So whether this is energy or not is not quite clear. It certainly doesn't have the right units, but we should interpret it as a constant that is related to energy. That's our second equation done. Now we look at the phi equation, where something similar will happen because nothing here is a function of phi. It only depends on phi dot. Phi equation, very similar approach. dl d phi equals d over d lambda dl d phi dot. The left hand side is again 0. Our right hand side is d over d theta. And if we look in to our Lagrangian, it is 2r squared sine squared theta phi dot. Where we recall that theta was pi over 2. Therefore, this object here becomes 1, which means we have d over d lambda 2r squared phi dot. Some of you might recognize this as a quantity that you might have seen before, which means again we can integrate. We call this constant of integration 2L. To r squared phi dot squared, and then we cancel by the 2 on both sides. And get L equals r squared phi dot. This looks like angular momentum. Angular momentum. Again, this is perfectly expected. We have a Lagrangian that is independent of the angular coordinate. It is a spherically symmetric system. In spherically symmetric systems, angular momentum is conserved. What you see, what is happening here is that because the Schwarzschild solution has so many symmetries, it is static and spherically symmetric, 3 out of the 4 geodesic equations are in fact very simple, and they're also very natural. They tell us things that we already knew in a sense, but it forces us to think about them more formally. So the first 3 equations mean we can choose to work in the equatorial plane. That solves the first equation. We identify a conserved quantity related to energy, which solves the second equation, and we identify a second conserved quantity, angular momentum, which came out of the third equation. Now you might think, well, we now have to compute the hard equation, which is the geodesic equation that involves the radial coordinate r. However, we can again be more clever and actually not do this. Let us substitute these 3 results back into L. We had L equals minus f of r t dot squared plus r dot squared over f of r, and here r squared theta dot squared plus r squared sine squared theta phi dot squared. This is one for theta equals pi over 2. Then we had that t was e over f of r, which you see up here. T dot is e over f of r. And here you still see that phi dot is L over r squared. And obviously this here also says that phi dot is 0. Therefore, our Lagrangian, if we substitute everything back in, we have minus f of r e squared over f of r, this whole thing squared, plus r dot squared over f of r, plus 0, because r dot is 0, and then plus r squared. This is 1, L squared over r to the 4, which we can now simplify a little bit. This f cancels with that f, and here you are left with an r squared, which means we have L equals minus e over f of r plus r dot over f of r plus L squared over R squared. This is now a very nice and simple equation, and what I do now is I simply rewrite this a little bit. And you will see that this equation, once I rewrite this, will all of a sudden look particularly nice. I multiply through by f of r. I get here then f of r, L, I'm moving this over straight away, minus f of r, L squared over R squared, equals minus E plus R dot squared. Some of you might see where this is going now. R dot squared equals f of r, L minus L squared over R squared plus E. All of a sudden you might think to yourself, well, hang on a minute, this is starting to look suspiciously good, which means we can now say, hang on a minute, this is 1/2, just multiplied all by 1/2, minus, I now put in my explicit expression for f of r, as the factor of 1/2 I just multiplied with, 1 minus 2m over r. Here is L minus L squared over R squared, and all this is E. Remember, E is a constant. And now I want you to stare at this for a few minutes. I'm just writing it out once more by flipping the sign of the last term over. What do I want you to see here? I'll write this in turquoise, nice color. What is the interpretation of a term like this in classical mechanics? Kinetic energy. And yes, you can argue that the mass parameter is missing. However, just think about kinetic energy and then you divide by the mass. If you interpret this sensibly as kinetic energy and you already spot that the right-hand side is a constant, then this must be interpreted as potential energy. And hence, it is perhaps unsurprising that this then becomes total energy, which is related to our constant E. Firstly, you see that E still doesn't have the right units of energy because the left-hand side isn't really energy. And there's still this factor of 1/2 here. So E is clearly related to energy, but you shouldn't call it energy. And you see that I'm able to write down the energy equation for our two-body problem without ever computing the geodesic equation for R. It's much more convenient doing it this way. You could write down the geodesic equation for R, which then involves second derivatives, and then you could integrate it once, which then would give you that equation. But this is a much more efficient way to do this. And by the way, I have just noted that I dropped, here is a little square. I just dropped this in my calculations, which just drums in the point even more that E is not easily interpreted as energy, but clearly is related to it. And so, for obvious reasons, we now define our effective potential to be this: 1/2 1 minus 2m over r, L squared over R squared minus L. And I want to multiply this out a little bit now, because I want to talk about the different terms a bit. there is one term here where you have L squared over R squared that multiplies the 1, L squared over 2R squared. We have a term where L multiplies 2m over R. There's a factor of 1/2 here, and there are two minuses that come together, which means what we get here is L m over R. And we get this mixed term here. Again, the 1/2 cancels the 2. There's a minus here, which means we have minus m L squared over R to the 3. And in the way I've written this, we are left over with the constant term, minus L over 2. It is natural to regard this as the potential energy or the effective potential. However, as you see, I could have moved this term 1/2 minus L to the right-hand side and then redefined my constant. This looks more elegant to me, but it is largely irrelevant of how we are calling this effective potential because it is only shifted by a constant. And what we will now do, we will just discuss very briefly those terms so that we know what they mean. Many of these terms should look very familiar if we compare them with Newtonian physics. Let us begin with the easiest term, Lm over R. You look at this, and if you look at it the right way, then you see this is the standard Newtonian term. In other words, the 1 over R potential. Remember that L is -1 for massive particles. Which means this term then indeed becomes minus m over R, which is the correct Newtonian potential. As it should. Our whole setup of general relativity was done in such a way that we can ensure that the Einstein field equations reduce in the limit of weak gravitational fields and slow motion to the Newtonian equations. And you see that this happens immediately in these geodesic equations. The Newtonian term is part of the setup. Next, we are looking at this term here, L squared over 2R squared. This is also a familiar term for anybody who has done the Newtonian two-body problem. This thing is usually called the centrifugal barrier term. We can neglect the constant here. That is again, potentials shifted by a constant are not particularly interesting for us. This is the interesting term here. This is the one that we should really be looking at, because this term has no analog or no equivalent in Newtonian physics. This coupling of mass and angular momentum is something that doesn't exist when you look at the corresponding Newtonian problem. And hence, we can really identify this as the new general relativistic term. You can really say this is the correction to the Newtonian problem. And it is really important to keep this in mind, because if we know that this is the term that distinguishes, or that is the new contribution due to general relativity compared to Newtonian physics, we know it will be this term that will in the end induce differences between the Newtonian and the general relativistic formulation of gravity. It is this term we always need to keep an eye on. If we make this term small, this is exactly the potential of Newtonian gravity. If this term is significant, we get some general relativistic corrections. And the idea will be, if you remember these potential problems, they're generally quite hard to solve, and the integrals involved are usually not doable exactly. And so you can already guess that what we will be doing is looking at this term and making a form of Taylor series expansion, assuming that this term is small. And then we will get the Newtonian theory plus the first order non-Newtonian correction. And this is the bit that we can then try to test. And all experimental evidence shows that this term is present, hence giving very strong evidence to general relativity. So the equation we'll be studying in the next few lectures, I shall write them now all down again so that we really have them. We have our equations are, we have our equation here. So we have 1/2 r dot squared plus v effective equals 1/2 e squared, which is some constant where v effective is L squared over 2r squared plus Lm over r. Then we have the interesting term ml to the 3 over r cubed and our constant term, which is not the interesting one. However, we will need also that L equals r squared phi dot, and we need our other equation E equals 1 minus 2m over r t dot. These are the 4 equations that we will need in the next few sessions. And if you wonder why we do need these equations, I can explain this immediately. What we are having here is drd lambda. This gives us the radial coordinate of our curve as a function of the affine parameter. From a practical point of view, we don't really want to work with respect to an affine parameter because this thing is arbitrary and we can rescale it. I mean, not the affine one, but in principle we have some parameter, and that parameter is not something we can easily access. However, using the chain rule, we can convert with these 2 equations, dr d lambda, we can convert this to dr d phi using this equation or dr dt using that equation. And it is those equations that generally help us to understand the geodesics in some concrete situations. And this is exactly what we will do in the next sessions. Thank you very much.